Okay, it's already recording. I'm so bad at this. I'm not a news person here, anchor, but I am trying to give you guys some videos so you can have this resource available to watch and review what we went over in class. So right now I'm going to share my screen and let's look at the X-ray tube, which is what we looked at the end of the day today. So the X-ray tube, and I noticed that the quality of this camera was kind of bad. I don't know if it was my computer screen or how it'll look on your end. It's not as clear as it is when you download this PowerPoint directly. So highly recommend doing that so you get better slides to look at. But the X-ray tube is the first part of our lesson. This is the real stuff, the important stuff, the good stuff of the class. So first today, we're going to look at the X-ray tube, and then we're going to look at what happens exactly when those little electrons slam into the target and X-rays are produced. More in depth tomorrow. But first, we have to know about how the tube works and what's going on inside of it. So the criteria needed for X-ray production, there's 4 things that are said to be needed: a source, a vacuum, a high potential difference, and a target. Those are our 4 things. We're going to break that down into looking at the construction of the tube and what those things do. So the construction and some terms that you need to know for this whole lesson. The housing, the tube housing, we talked about that as being the surrounding area, that's what we see when we walk in the X-ray room and we're looking at an X-ray tube. We have 2 sides to our X-ray tube, the anode and the cathode side. On the anode side, we're going to talk about these parts: the stator, the rotor, and the focal spot. On the cathode side, we're going to talk about the filaments and the focusing cup. Some special terms that you are going to be needing to know what these things are and what they mean: thermionic emission, space charge effect, line focus principle, and anode heel effect. And we're going to go over those in depth as we get to them. And there's some concepts, and they're in your textbook too, but I kind of have them in this order that we're going to talk about them. So here's a little diagram drawing of the tube. You will have to label and fill in some parts to the tube. So you want to know this is going to be your little friend for this chapter. So on the anode side, we call the anode side the positive side of the tube. That's the rotor and stator assembly, the target, the disc. That's what's on the anode side. On the cathode side, we call that the negative side of the tube. So you'll see that little negative symbol on the tube when you look at it in the room. The negative side of the tube is the cathode side, and it holds the filament. And the filament is inside of this thing called the focusing cup. Around the parts to the tube, we have this thing called the glass envelope that supports, that holds it all in there and keeps it in a vacuum. There's a little area called the port or the window area. Some books call it the window. That's where the X-rays are coming down out of. Here's another drawing showing you the X-ray beam coming out, the electrons coming off the filament. We talked a lot on this slide today. We talked about those rotors and the bearings in there. We talked about the stator, which is the electromagnets that go around it and spin it. We talked about the disc, the tungsten anode is what it's called, the anode disc. We talked about some of the parts and the metals that are in it. So we're going to go through that real quick here again for you. Electrons are being boiled off the filament at the cathode side. They're heated up, boiled off by that Ma for a certain amount of time. That's our mass side of the tube through the filament circuitry. Over here on the positive side, we have the kilovoltage coming in. That's the kVp side of the tube. The kilovoltage peak, kVp, is our potential difference, that high potential difference, that positivity we're giving to the anode side of the tube to allow those electrons to be attracted over to that side of the tube to hit and slam into the target. When they do that, X-rays are created, and that's tomorrow's lesson, what's happening at that moment. But X-ray beam comes out in a big fan pattern, and it goes in all directions, but we see it drawn coming out like that path through the bottom, through the window to come through our patient. All right, we're going to break this down a little bit more. The anode side. Let's talk about the anode. Mostly what we want to talk about on the anode side is that actual part where the X-rays are being made, where the electrons are slamming into that disc. It's positively charged because that's the side of the tube where the positivity is going to be to attract those electrons over. Basically, that disc receives electrons. We can say the electrons bombard it, slam into it. There's two types of anodes or two types of disc, a rotating or a stationary, depending on the tube. Most of our X-ray tubes at the hospital are going to rotate. That letter A there, that top one is a stationary tube. It does not spin. It's just a chunk of metal sitting there. Letter B is a disc, kind of similar to like a little frisbee, spins around and rotates inside of our tube. On some components that we saw in the picture there, we have some things we want to be able to say what they are and what they do. We have a stator and rotor, and we have something called a focal spot. Stator and rotor all has to do with that special rotating anode, a stator rotor assembly. The stationary does not have that. So the rotor, R for rotates, it rotates. That's that part that's kind of dark gray back here. Has bearings in it to help it rotate. The stator is outside the glass. It's electromagnets. We're going to look at that in a minute in a picture that help it to rotate. Focal spot is the actual area where the electrons hit. We call that the focal spot. All right, some more stuff about that stationary versus rotating. Stationary are in some older X-ray tubes. Usually we could see those maybe at a dental office. They're basically just a big chunk of metal. Tungsten is our metal of choice, embedded in a copper rod. Copper is used for the thermoconductivity of the electricity going through it. Primary disadvantage of that and why they invented the rotating anode is to avoid this thing called pitting, where those electrons are hitting that same area over and over all day long. Turns out it digs into the metal and pits it and causes a divot and makes for uneven X-ray production. So that's its disadvantage, that same target area getting hit all day long. So rotating anodes help get rid of that. The rotating is what we see in general X-ray tubes today, better for heat dissipation. That avoids the pitting of the anode. Purpose of the rotating anode is to spread out that tremendous heat that's going to be produced during X-ray production, spread it over a larger area for us. That disc is made out of this metal called molybdenum, maybe better pronunciation, as a core coated in tungsten, mounted on a copper shaft with that moly core. That core is a little bit lighter, makes it a little bit easier for it to spin and rotate, not as heavy as a metal. The rotating anode spins almost 10,000 RPMs. So really, really fast it's rotating in our tube. So sometimes we can hear that rotation. It's rotated by induction motor. It's called EM induction or self-induction. Kind of doesn't have any parts connecting. It's that magnet rotating around it. The picture in the book kind of displays it like this, the rotor in the center with magnets rotating around it or turning on and off that negative and positive charge to them to rotate them. It's electromagnetic induction. So these are electromagnets that we're working with, very strong magnets to get that to spin to that 10,000 RPMs. So the rotor is located inside the glass envelope. When you held the tube in your hand, you probably were holding on to the actual rotor. This part here, that dark part. We turn it a little bit. Don't know if you can see it in the video, but I can kind of feel it spins if you do it really fast. I can't really see it too much. It barely moves. You can see that it's a copper to it inside there, that copper inside the shaft. The stator would be where my hand is. The magnets would be around the outside of the glass. So rotor inside the glass. On that rotor is the anode disc at the end to spin. The stator is the electromagnets arranged in pairs around the rotor located outside the glass envelope. Does not touch it, but it turns it by electromagnetic induction. They're energized, induced by electric current, which in turn makes that rotor spin within that magnetic field. This is how we rotate and spin our disc to help dissipate that heat. Very important concept. That target disk area, that actual round disk itself, has also got that metal moly. I need to Google this pronunciation because I always say molybdenum, but moly for short. It's the back side of the disk, the core. Low thermal conductivity, very light but strong metal, not as heavy. So our tube has some lightness to it so the disk can spin better. Outside of it is still coated in the tungsten. W atomic letter to symbolize our tungsten on the atomic chart with a number or a Z number, atomic number of 74. We want a high number for lots of electrons in that shell for efficiency of X-ray production. That'll be more coming tomorrow. Copper is in part of the shaft, also copper here for that electrical current that's coming through. So we talked about this disk being called the target, the anode disk. On that area, there's an exact place where the electrons are going to hit. This is the actual target. We're kind of associating the name target with the whole disk, but really it's that area on the anode disk where the electrons hit. So the impact point for the stream of electrons is where X-ray photons are produced at the target on the anode. That helps you on the anode disk. Some other names for that target area. Love to give us 5 names to remember. The target, the focal point, the focal spot, the focal track. Focal spot a lot of times is also used besides target. Now on the other side of the tube, we can't forget, we have to have a source. That's our cathode side of the tube, the negative side. It's negatively charged. Electrons are negative. All of our negative little electrons are going to be put across that filament circuit to come and be boiled off of. Our filament provides our source for our electrons to come off. We have 2 filaments really in most of our tubes. It's called a dual filament tube. We'll talk about that on the next slide. We have a large and a small filament, so 2 little wires, coils of wire, the filament. Inside that cathode area, the filaments sit in this thing called the focusing cup. It's a little divot, a dip down area. Here's a picture of it. So most of our tubes have 2 filaments, a small and a large. Some older tubes may only have 1. Those little wires are also made of that fancy little metal called tungsten with a tiny little bit of thorium added for this thing called thermionic emission that's going to happen. And we're going to talk about help produce those electrons out for us. So that one is so small in that picture, I can barely see it in the real picture here. So we have 2 little shaped filaments inside the focusing cup. So it's a dip down area that the filaments sit in, focusing cup for them to sit in. I think we're going to talk more about that on the next slide. So the filaments sit in the focusing cup. The filament is heated up to this fancy term called incandescence. That means we are getting it really, really hot so it glows white. Just like when something heats up in a fire and it starts to glow. When that happens, small parts of that filament are being burned off. We call that vaporizing away, creating a gassy tube, and therefore eventually could mess up the vacuum of our tube and our tube could go bad. That's how I got mine. It turned it into a bad X-ray tube. Now, thermionic emission, a fancy word for just saying that we are boiling off electrons. So we heat that filament up till incandescence and little electrons become boiled off of it. This occurs at the cathode on the filament. There's a cloud of electrons that's formed there. This is called the thermionic cloud. Here's a little picture of it. Our little wire with our electrons just navigating there, little negative charges sitting on the wire being boiled off. So this is where the focusing cup comes into play for us. It's made of nickel. It surrounds the filament. It has a slight negative charge. So that negative charge of the focusing cup helps to keep our little cloud into place with those little electrons, helps forms the cloud. Another name for that is the space charge, and that's because we have a thing called the space charge effect. Space charge effect means that once that cloud reaches a size equal to that of the current we selected on our control panel, no more electrons can be boiled off. Space charge effect. That's why the cloud is called the space charge. They give us 3 names for everything. Our limit on our tube that we need to know is a maximum of 1200 MA. So we're setting our MA, our milliamps, for a certain amount of time to give us a mass. That is our total amount of electrons we need to be boiled off, our number, our quantity on our tube. Tungsten's been talked about a lot. We love tungsten. It's both on the anode and the cathode. And reasons for it is basically right here. High melting point, 3400 Celsius, 6152 Fahrenheit. Should have put that on the quiz. It'll be on your exam. High atomic number, which enhances the production of X-rays, and a big thing with that is heat thermal conductivity for heat dissipation across our tube. We're going to talk about this tomorrow, but I'll go ahead and throw it in this video so I don't have to make another one. We stopped right here at the protective housing. That is the lead-lined metal structure. It's around our actual glass envelope of our tube. Now, I do know I say glass envelope of the tube, but I know some tubes can be metal too. But we still have a protective housing that's lead-lined because that is important to keep us from getting a leakage radiation. And our requirements, regulation is 100 milliradians per hour at 1 meter, which translates into 0.0258 millicoulombs per kilogram 1 hour at 1 meter, which starred here for you for the registry because now they're doing everything in the new system. So instead of that weird millicoulombs, we can say 1 milligrade at 1 meter per hour. Woo! A lot of words there for that. When I look it up online, the 100 milliradians per hour at 1 meter is still listed by the NCRP as the recommended amount. So I don't want to get rid of that, but I do want you to know the 1 milligrade at 1 meter is what I'm going to test you on, and the registry should be testing you on that. If you see it anywhere written in any books or online, it's going to be the 100 milliradians per hour at 1 meter until everybody gets caught up with this new registry wording, unless they lied to us. So I'm going to give you both so you know both. 1 milligrade, 1 meter per hour equals out to the 100 milliradians at 1 meter per hour. That protective housing helps to keep our tube secure. It houses it. It has a cooling fan in it. It has an oil bath in there to help with all that heat that's going to be produced. So when we touch it, we usually don't feel it getting too hot, but possibly that if you use it a lot and have a lot of exposure, it could get kind of hot. But some things inside that protective housing you do want to know. There are fans there. There are things in there. It's a dialect oil, kind of what's inside engines. Helps dissipate the heat and keeps us away from some thermal damage. 2 cautions. It can be rather hot. The high voltage cables should never be used as handles to maneuver the tube head. Common sense. Thousands and thousands of volts, guys, going through these tubes. We do not need to be pulling on them. We don't want to cause any kind of error. The glass envelope, I talked about that earlier. That's to maintain the vacuum for our tube. We do have 2 types. I have seen glass types. I've never been shown a metal envelope type, but the glass envelope is generally what you saw with my tube is a Pyrex glass. It's very heat resistant. Anybody know about Pyrex casserole dishes? I'll talk about that in class. As the tube ages, it can become vaporized. So that's why they moved on to this metal type. It helps extend it, avoids that problem of the gassy tube. We call that arcing. Both of them have a little window, a thinner spot for the X-rays to exit through so it doesn't absorb them as much. Ooh, big principle, line focus principle. Should I actually do this on the video? I guess we'll try it. This little thing about when you've seen the pictures of our anodes, they were slanted or angled. That's because of this line focus principle. Similar to an artist easel, I like to think of when you stretch it out, how the easel turns and angles. It creates a different degree from this top point to the bottom point of the slant, rather than here and here. Here and here, I have a wider degree of angle, and our beam comes out in a fan. So the line focus principle is going to give us the face of the anode target and the actual focal spot and an effective focal spot, blah, 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 blah. Actual focal spot and effective focal spot are actually two separate things. What do you think the actual focal spot is? It's the actual area where the electrons hit. Or the effective focal spot is what is most straight up and down of our beam instead of that fanned out part. So I'm going to see this on a picture in a minute. So that means that no matter what, we're always with an angle going to have a different sized area where the electrons hit than the area that's the effective focal spot. So the area that the electrons hit is going to be larger than that straight area, a small effective focal spot. You might say, why does that matter? Ooh, this gets into some geometric stuff that we're going to talk about in the future in another whole chapter. But we want to have this ability to change from a smaller electron stream and a larger stream of electrons because of what's going to happen on our image. The closer we can get our beam to be tight and straight up and down together, the better it's going to be able to translate into a direct, no distortion on our image, on the image plate. So why wouldn't we just have everything the best possible? Sometimes we need to cover a bigger IR size, so we need a larger one. We'll talk about that more in class tomorrow, but know that actual focal spot is where the electrons hit. The effective focal spot is the beam coming down out of the tube. We're going to have a larger actual focal spot to make it hit a bigger area on our target disk, but we want, this is kind of weirdly worded on here, a smaller effective focal spot. So let me show you that in a drawing. Here's two different anode angles, a 24-degree and a 12-degree, and you can see the electron beam coming across and hitting it. And we're going to measure that, and we draw it out on the board, and then we can measure from top to bottom on it to see where our beam is coming out with our central ray, and these are our effective focal spots. And that basically is the line focus principle in a nutshell. We'll talk about that in detail more in class. The general target angles for our disc is going to be between 7 to 18 degrees according to our book. Most of ours are 12 degrees. That's our most common. And I think we just have a few more slides. We'll probably do another video for these because that's a lot right there. Let me pause this recording. Let me try to get back over to figure out how to do that. Stop share.